Welcome back to another explainer. You know, if you've ever actually stopped to think about the simple act of taking a breath, you might be totally surprised by the complex engineering, physics, and mathematics happening inside your chest right at this very moment. Today, we're traveling from macroscopic anatomy down to the microscopic cellular hurdles of gas exchange, and finally into formulas that dictate our lung capacities. It is a brilliantly designed system, and I promise you, by the end of this, you're never going to look at a simple breath the exact same way again.
Here is our roadmap for today. We're going to start with the architecture of the lungs and the microscopic exchange zone. Then we'll move into the mechanics of breathing, measuring pulmonary volumes, and finally, calculating lung capacities.
Section 1. The architecture of lungs, the protected thoracic cavity.
Our lungs sit inside a highly secure anatomical vault, surrounded and shielded by the vertebral column, the sternum, the ribs, and the diaphragm. But take a look at the inherent asymmetry of our bodies. It's kind of wild, but your two lungs, they aren't identical twins. The right lung is divided into three distinct lobes, the superior, middle, and inferior, separated by horizontal and oblique fissures. But your left lung, it only has two lobes. It's slightly longer, sure, but it literally sacrifices that third lobe to create a specific notch. Why? Well, just to leave room for your heart, which tilts slightly over to the left side of your chest.
300 million. Let that sink in for a second. Deep inside those lobes, the airway branches down until it ends in these microscopic air sacs called alveoli. Between your left and right lungs, you have roughly 300 million of them. That creates a surface area roughly the size of a tennis court. And that's all just to ensure your blood can grab as much oxygen as humanly possible with every single breath.
Section 2. The microscopic exchange zone, where the actual gas exchange happens.
Now, for an oxygen molecule to actually make it from the inside of your lung into your bloodstream, it can't just magically teleport, right? It has to physically jump through three specific structural hurdles, which together are known as the respiratory membrane. Step 1, it must pass through the squamous epithelium, which is the thin outer wall of the alveoli. Step 2, it crosses a middle basement membrane. And Step 3, it penetrates the endothelium, the inner lining of the blood capillary. Because these layers are incredibly thin, oxygen can just pass right through them via simple diffusion.
What's absolutely fascinating here are the specific cells making up those tiny alveoli. Type 1 pneumocytes handle that gas diffusion we just talked about. But type 2 pneumocytes, they have a mind-blowing job, secreting a chemical surfactant called lecithin. Think of the alveoli like tiny wet balloons. If you deflate a wet balloon, the sides are just going to stick together because of surface tension, and good luck blowing it back up. Well, lecithin acts as a lubricant that actually reduces this surface tension. Without it, your alveoli would literally collapse and stick shut every single time you exhaled.
Section 3. The mechanics of breathing, the physics engine driving our breath.
Okay, so the crucial mechanism here relies entirely on Boyle's law. It states that the pressure of a gas is inversely proportional to its volume. Basically, if you increase the volume of a closed space, the pressure inside drops. If you decrease the volume, the pressure shoots up. And gases will always naturally flow from an area of high pressure to an area of low pressure. Keep this rule in your back pocket because your body literally relies on Boyle's law to keep you alive.
Let's look at how our body actually manipulates Boyle's law. During normal inhalation, your diaphragm contracts and flattens out downwards, while the muscles between your ribs pull your ribcage up and out. This physically increases the volume of your thoracic cavity. And remember Boyle's law? More volume means less pressure. Because the pressure inside your lungs drops lower than the atmospheric pressure outside, air naturally rushes in to fill the space. On the flip side, for a normal exhalation, you don't even have to do any work. Those muscles just simply relax. The cavity shrinks, volume decreases, pressure spikes, and air gets pushed out.
I want you to actually engage with this next concept for a second. Go ahead and take a normal breath in. Okay, that was active. You used your diaphragm and external intercostals. Now let it out normally. That was completely passive, just pure muscle relaxation. But now take a breath, and I want you to forcefully push every last bit of air out of your lungs. Push it hard. Do you feel your abdominal muscles tightening up? That proves that while normal exhalation is passive, forceful exhalation is a highly active process. It requires a whole new set of muscles, the internal intercostals and your abdominals, to literally squeeze that thoracic volume even smaller.
Section 4. Measuring pulmonary volumes, putting numbers to our breath.
We measure exactly how much air you are pulling in and pushing out using a clinical instrument called a spirometer. When we compare these volumes, notice that tiny 500 milliliter bar on the left. That is your tidal volume, the air you move during a normal, relaxed breath. But look at the massive 3,000 milliliter bar on the right.
That is your IRV, your inspiratory reserve volume. This shows us that on top of your normal tiny breath, you have a massive extra reserve space in your lungs so you can forcefully inhale a huge gulp of air if you suddenly need to run or exert yourself. Similarly, you have an expiratory reserve volume, or ERV, of about 1,100 milliliters that you can forcefully push out beyond just a normal breath.
But check this out. Here's a truly surprising fact about that normal 500 milliliter tidal volume you breathe in and out while resting. Not all of it actually makes it to the microscopic exchange zone, because your airways, like the trachea and the bronchi, are essentially just hollow pipes. About 150 milliliters of the air you inhale just sits in this anatomical dead space, doing absolutely nothing. Only 350 milliliters actually makes it all the way down to the alveoli to exchange oxygen with your blood.
Section 5. Calculating lung capacities. The mathematics of respiration.
So let's see how these capacities build logically upon the numbers we just learned. Your inspiratory capacity is the absolute maximum amount of air you can inhale. How do we find it? We just add your normal tidal volume breath plus that massive inspiratory reserve volume. Expiratory capacity is exactly the reverse. Tidal volume plus your expiratory reserve volume. But the most crucial calculation of all is your vital capacity. By adding your tidal volume, your inspiratory reserve, and your expiratory reserve together, we find the absolute maximum limit of air that you can actively manipulate and exchange in a single, massive, forceful breath.
To wrap up our explainer today, I want to leave you with a provocative thought based on everything we've just uncovered. We know a spirometer measures the air moving in and out, right? But which lung volume can a spirometer never measure? Think about it. The answer is the residual volume, or RV. No matter how hard you forcefully exhale, even if you squeeze every single abdominal muscle you have, roughly 1,200 milliliters of air always stays behind in your lungs. It literally never leaves. Why? Because if your lungs ever completely emptied, those 300 million tiny alveoli balloons would permanently stick together and collapse. Your body mathematically ensures you always keep a safety reserve, sacrificing maximum efficiency just to guarantee you stay alive. Incredible, right? Thanks so much for watching this explainer, and hey, don't forget to take a deep breath.